Morning, everyone, and welcome to Astronomy 100. Today is actually September 20th, and we are doing, I think, week 6, and we're going to cover a few topics in it. So let me get the materials going first of all for it. I want to get into the page and then make sure I am in the student view so that we have the same look at things. Okay, so I have week 6 and I also have week 7. So let me get into share screen. Again, this week is extremely important. We are actually at a very, very important mark of the class. You must have received a message from me this morning around 7 a.m. concerning the grades. The grades have been basically weighted the way that the syllabus indicated that they need to. So you must have seen change in your overall grade average, okay, reflected by this weighting system. However, this weighting system is missing two critical pieces in the puzzle. And the two pieces are, the first one is actually midterms. And by far, it weighs the most. And it has the most impact overall the grade. Since we don't have really a midterm, I wouldn't really qualify the averages at this point as being reflective of the overall progress in the class. But since we have a midterm starting next week, then the grade should really be reflecting of how we're doing in this class. So that is an important message that they sent this morning. And the message also has in it another issue that I noticed with the homework assignments. First of all, in terms of team working, some of you actually can compare the two work and they see that there is a lot of similarity between them. Actually, sometimes they're copies, replicas of one another, except the students failed to mention the fact that they worked in teams. So I basically did not do a big fuss over it at this point, but I really am going to emphasize on the fact that you need to mention who are you work with. This is critical. It is not that you cannot work with people. As a matter of fact, you are encouraged to work with people, with your classmates, except that you have to be fair and tell me who you worked with. That's all, okay? And you will get your full credit for whatever you did. So there's no problem. So that was one of the issues that I noticed, and hopefully you guys will take care of that. The other problem that I ran into is some of you received a mark of 0, and it shows that they have a link there for me to go and see their submission, except the submission is not actually on Canvas, but rather on their Google Docs, okay? Of course, they did not make that document available for me or for anybody to look at. It's still private with their own basically account. And at this point, I have no access to that file. So I cannot really see what you did, and I could not really give you a grade whatsoever. So the only grade possible in there is a 0. So we really asked you, and I put a message in the grading there, and please pay attention to the messages I put there, that I need access to this file if you want me to grade it. So this is a forewarning. You still have another homework that is due and more homework that are due. And in terms of weight, homework was the second immediately after the midterms. So it's really something that you guys need to take care of immediately. You can convert Google Docs into PDF files and upload the PDF file to Canvas. I'd rather really see your work on Canvas no matter what, because of later reference. If down the road, for example, you would want me to look at something or you would want me to compare something, I really want it on Canvas for your record as a class record, rather than sitting on your Google Docs, because then I will have no access to it. And if in case we want to discuss a grade or something, and you probably something happened to your account or you don't access it anymore or something, we lost it. We cannot do anything with it. So again, I don't want Google Docs at all. And if you have to do it, you must really convert it to a Word, sorry, not a Word file, to a PDF file or any other format you like, and put it on Canvas so that we can have a place there where we can refer to. So those are some of the issues I raised in that message. And the biggest deal, of course, is the review for the exam. This is by far the most important thing, okay? So this week, we have the unit as normal. We have the objectives I'm going to go through. We have the review from the previous week. These are the main points that I think are important. It doesn't mean that the others are not, because you will be tested on everything. And again, the discussion that is going to be generated today and the link that is going to be generated today from this video, from this recording, is going to be posted in here. For those who are watching this recorded, they already have accessed it through this link, okay? And then the units we're covering are units 37 and 38, which closes the book on the 1/3 of the class, okay? So by now we have 33% of the materials covered. And this is the extent with which the first midterm will cover, up to unit 38, okay? Of course, we skipped some units. So the units that we covered are the ones you are responsible for. So if you see a unit that is not mentioned, those are not going to be covered in the exam. So the exam covers up to unit 38, and these units are all on Canvas from week 1 up to today, week 6, okay? For some of you who are reading the captions, because I do the captions and I rely on the auto captions, and then I try to fix it. So if you find something issue with it, because sometimes they say things that probably the caption doesn't capture. Yeah, I'm here. We're here. Anyway, the thing with it is, please. Sorry, did you say something?
Yeah, can you hear me?
Yes, we can hear you. Yes, and the class is on. Can you hear us?
Yeah, yeah. This is
Oh,
Paulo Valencia. I don't know if you've
yeah.
seen my inboxes
Okay.
and all that, right?
Hold on. We are in the middle of a session right now, so if we're going to discuss something related to a specific item, we can do it later on. Okay.
But can I
Ready?
tell you something? Since it's like no one in the Zoom meeting, like there's only 2 people. Can I tell you real quick?
Okay. It is recorded. It is recorded, and it's going to be posted for the entire class. We cannot
Oh,
really
it's
discuss it.
recorded.
Okay. We
And,
can do it later.
okay. I'll send you an email. All right.
That's fine. Yeah. Okay. Thank you. Okay. Very good. So again, this week is of extreme importance, and I'm hoping that everybody focuses on the exam. Okay. And so we have the this session here, and I'm sorry, I'm distracted a little bit. So again, we have the midterm that is coming next week. The midterm is here, okay? And this is the review for the midterm. The way it works for the review, and this is the item that I'm going to ask you guys to basically remember from this week as an item of discussion, is the fact that you have to do the review in order to receive the full marks for it of 120 points. Regardless of what you score in the actual review, you will get the full credit for it. And the credit goes toward your participation, okay? So if you score, let's say, for example, 10% in the review, you will get 120 points. If you score 110 points in the review, you still get 120 points. If you score any score, it doesn't matter, you're going to receive the full credit for it, as long as you do it. If you don't do the review, you will get a 0 mark in it. So it is graded, and it's an important assignment, and you can get a lot of points out of it if you just do it. The reason why it's important, again, to do this, and I encourage you actually to do this and take advantage of this offer, is because of the fact that the midterm is coming next week, and this is a way for you to ready yourself for it. As I was saying before, the midterms are weighted extremely heavily in this class. So this is basically geared toward that, to prepare you for it. So take it seriously. I know it says to take it between, the time allotted is between 2 to 4 hours. Some of you who have been following so far and have the book and have all the resources basically necessary and doing things, it might take you less. Some of you who did not have the resources and basically they're barely getting into the materials, it might take you more. But on average, it should be 2 to 4 hours. Again, the review is about 2 to 4 hours. The actual exam should be a lot less than that. Actually, it's timed and it's 85 minutes actually. So, and built into the 85 minutes is a 15-minute review for your questions. So you have time to basically go through it and do the exam, and then actually have time to review your questions and submit it. If you don't submit it, the Canvas will submit it on your behalf. So it's very important that you do the review, at least finish all the questions. And so this is important. So what I'm saying in here is that we have to do the review, okay, to receive full credit. So I'm going to type in here what I'm saying in here. So do the review before the 29th, because the due date on it is the 29th of September for full credit. If you don't do it you are not going to get the receipt for full credit. Of course, I put this one on the chat. For those who are not attending live, of course, they will not be able to see the chat, but hopefully they will pick up the item. And that is to do the review on or before the 29th of September, which is next Wednesday, actually, if you think about it. You have about 10 days to finish it. To receive full credit, no matter how much you score in it, you're going to get full credit for it. If you don't do it, of course, you get no marks, and that's not good. So you're really encouraged to take care of this review. On the 30th, which is the Thursday, the day after this one closes, this one is due, the exam will be available. And it will be available from Thursday. So I encourage you immediately to take the actual midterm next week, okay? When it's available on Thursday. This is the trouble. Sometimes we delay things, and then we get into a problem down the road when things started to happen, when the problem with the internet becomes slow or probably not available, power outages, other emergencies at home and probably at work and things like that, and they get us distracted. So we really have to take care of the exam as soon as it's available. So if it's Thursday, you are available for about 2 hours because it's 85 minutes, then that is the time when you sit down, grab your cup of coffee or whatever really you enjoy, and then start the exam if you are ready for it. And if you did the review, you should be, okay? If Thursday you're not available for some emergency reason or work-related or some other matter, then Friday is, okay? Which is the 1st of October. And if for some reason those 2 days are not convenient because boss and work and other matters, then really Saturday is the day, October 2nd. Unless you have really an impeding something that really at that point have pushed it too much. And now it's Sunday, October 3rd. And if October 3rd, for some emergency reason, and you pushed it to actual due date, which is October 4th, you really are playing for fire, because at that point, all kinds of issues start to happen. So again, midterm is important for the class. Midterm, you have to take it. Midterm will impact drastically your grade, okay? So do take it and take it seriously and take it as soon as you can. The review is here to help, okay? The review is here to help you prepare for that. And that is the item of discussion today. So this is the big deal that is happening this week, okay? Other than the fact that these 2 units are still required for the exam, so we have to cover them. Okay, since I made a big fuss over this too, hopefully everybody is already. There is another type of assignment that you're going to see. Remember, projects are also included in your overall grade, and they have their own weight, okay, albeit not as high as a homework or an exam or a midterm, but they still have their own weight. So we're going to talk about this one extensively from this point on, from next week on, and it can actually still have a little bit of leeway when it's due. So we're going to talk about how that is structured and what needs to be done to make it and to do it right. We will have 2 more projects, basically this one and in choice with another one, and then another mandatory project. Okay, so again, let me get into this week's objectives to talk about the topics, okay? Again, the first item in here in the objective, what I was talking about, the fact that the review is available, and the review, there is no time limit. So you can, if you need more than 4 hours, you're more than welcome to spend as much time. There is no limit on how many attempts you can come to it. So you can take as much time as you want. So there is no pressure. And it's graded for participation, regardless of the score you score in it, you're going to get the full mark of 120 points. If you don't do it at all, that is when you get the 0, okay? I don't recommend that you do that, okay? So this is basically the first item. And then the other two items are the units for this week. So what are we covering this week? We're covering two ideas. The first one is the planet as a rock, as a ball, basically, and the rigid structure, if you wish, of the planet, because it's an inner planet, and the planet Earth is actually a rocky planet, and it serves as a model for the rest of the other rocks, basically for Mercury, Venus, and also Mars, and to some extent also for the Moon or other basically planets when it comes to its internal structure. Okay, that's how that is. And then the second part, we're going to deal mainly with the atmosphere of the planet, and that actually serves as another model for another structure of different planets that have thick atmospheres or have a lot of atmosphere. Okay, so that is like Jupiter, for example, or Saturn, or the other outer planets. So this is basically how, because Earth is available for us, it is within our reach. We can test it, we can analyze it, we can observe it, we can actually send probes to it, I mean, underneath and up in the atmosphere and so on and so forth. And we can study it, get its temperature, get its pressure, get its density, get its structure, get all kinds of things, the different properties that we can think of. And those are the physical properties and the chemical properties. Based on those, we can build a model for the other planets and see how they look like, okay? And maybe we'll have an understanding of what's going on. So that is the idea behind these two units. Okay. In terms of structure, first of all, how can we be sure? The way we study the Earth is mainly through earthquakes. I mean, what I'm talking about is the inner structure, because digging thousands of kilometers underneath the surface of the Earth is not possible. It's too much, okay? So what we do in this case, we study waves and how they propagate in different media, and based on this propagation, namely two characteristics, or several characteristics, I should say. The speed with which they move, and the amount of, and how they interact on surfaces, basically, how much is reflected and how much is refracted or transmitted to the other side, basically. So that's basically what is going on in this case. Since the Earth already has its own, basically, mechanism for doing these waves, namely through earthquakes, then we take advantage of those. There are two types of waves when it comes to the Earth. There are the so-called P waves and the S waves. P waves are compressional waves. Like I have this link in here. If I click disturbance in here, the disturbance actually is followed, is this compression in the string, followed by this rarification. So on one side, you have a bunch of rings coming closer together. On the other side, there are a bunch of, the rings are actually widely spaced, and so on and so forth. And this disturbance that travels along the length of the string is slinky. So we call this one compressional waves. We also call it longitudinal waves. Why do we call it longitudinal waves? Because the wave itself, which is the disturbance, travels along the slinky, along its length. So it's called longitudinal waves, okay? As opposed to transverse waves. If I click a disturbance on this side, this disturbance travels sidewise, goes back left and right on the string. It does not go, I mean, the disturbance is like this, but the wave is actually traveling from the top to bottom. So in this case, the direction of propagation of the wave, which is along the slinky, is perpendicular to the actual disturbance, which is perpendicular to that. So we call this waves transverse waves. In the case of the Earth, actually, this type of transverse waves are actually shearing waves. Like you take, for example, a piece of paper, and you try to slide one side over the other. So basically what you do in this case, you have to cut it and slide it one way or the other. So this is a shearing effect. And that's where the S is coming from, actually. It's coming from the shearing effect, shearing wave, the shearing, basically, wave. It goes like this. So if you try to take a solid, for example, and you try to shear it with enough force, you will. You can create this disturbance, and it basically, as long as it does not destroy it completely, the disturbance will travel from one area to the other. But if you see earthquakes, they usually are associated with a fracture in the upper surface. So there is that effect there. Now, in addition to that, the problem is when the medium is solid, you can produce shearing waves. However, when you are in a liquid format and you take an upper part of the liquid and you move it, it's going to slide, especially with enough force and speed. And the other one stays in its place, more or less. May displace a little, but not as much as the other one. May displace, and then the wave actually is attenuated. The wave is actually killed when it reaches liquid surfaces. Okay, so in this case, what's going on? Earthquake happen at a point. Let's say, for example, where I'm sitting in here. And if I have detectors every which way, the detectors every which way, once the wave hits them, they can zero in on the source. Okay. And also, in addition to the fact that the P wave and the S wave travel with different velocities, so it can accurately tell exactly where the wave is. Okay, where the disturbance started from, where the source of the disturbance starts from. Well, that is on the surface, but the wave, of course, travels in a 3D shape, and it goes throughout the entire planet. And it goes from point to point. Once it reaches where that type of medium is separated from a different type of medium, let's say, for example, with different densities, one is denser than the other, then in this case, part of the wave is reflected and the other part is transmitted. And the way it breaks down, actually, the way it's transmitted, it's going to be diffracted. So if it was incoming at an angle like this one, it's not going to continue at that angle, depending on the density. If it's higher or less, it's going to be it's going to be diffracted either inward or outward. So now I have a way of finding the density, and just by studying how much diffraction is happening between the different media. And if I know the density, I have an idea of what makes up that layer. So I find exactly the thickness of the layers based on the reflection, and based on the angle of refraction, which is going to be reflected backward again. That's how I find it. I will find exactly, or at least I have an idea of the densities. And if the density is around 8 kilograms per cubic centimeter, then in this case, I know iron is the one that is the main component in there. And if the density is higher or lower, I will know exactly what makes up that layer and how thick it is. So that's how we study the structure of the Earth. Okay, and if in case we reach a place that is molten rock, then in this case, the shearing waves will not be transmitted. So we know in this case that this is liquid region, and depending again on the angle of refraction, we can find how much liquid there is. If it's too liquidy, then in this case the temperature, we can find the density, the temperature based on the angle of refraction. So we can study a lot just by doing this. Okay, and again, the core itself, which is solid due to the extreme high pressures, the density, there is actually another transmission in there, and the refraction is going to happen at a different angle because of that. So that is going to tell us that, hey, we reached the solid, and this is how much it is, and this is how much density is. That's how we found out that the core of the Earth, the inner core, is made up with the iron and nickel, basically. Okay. So we know a lot about the structure of the Earth based on the earthquakes. So that's how we modeled actually our understanding for the rest of the solar system, at least when it comes to Venus, when it comes to Mars, and when it comes to the moon, and when it comes to actually also Mercury. When it came to Mars, actually, we have another thing that happened in 2017, and that is we sent actually in early 2017, we sent actually a lander there called InSight, and the InSight itself actually anchored probes into the surface of Mars, and that is actually not moving. It's not a rover, really. It's actually a lander. That's all. It did not have wheels. So once it landed in a place, it anchored itself and stayed in there. The point of the InSight is to study actually the Mars quakes as opposed to earthquakes on Earth. And initially, it had some difficulty because of the probe not properly going into the proper place and where it needs to be to collect data. But then at the end, we're getting a lot of data. So again, our understanding of seismology on here on Earth and how earthquakes basically happen on Earth helps us understand what's going on in the other planets. And that's how we know the different structures of the other planets. For example, we think, based on our understanding of the source of heat for the Earth, which is really a radioactive phenomenon. And radioactivity has to do with the amount of matter. The more of it you have, the more it takes for it to decay, the longer the time. And this is really the source of the heat for the planet Earth. But because Mars is a lot smaller than the Earth, and because Mercury is a lot smaller than Mars, we think that this process ended, at least for Mercury, a lot earlier than anything. And that explains the surface cratering that happens actually on Mercury versus what's going on in terms of Mars. Mars actually had a little bit more material, so it had more time for its subsurface to have high temperatures. And because Mars is spinning super fast, just like the Earth does, I mean, it goes 24 hours around its axis. So with a molten, basically, inner core, that produces enough current in it, and that current is what produces magnetism. Because any magnet that we can think of, like this magnets, they have a bunch of them in here. Any magnet that you can think of is what causes its electricity. So you're asking, where is the electricity coming from? In this case, it's atomic electricity, electricity on the level of the atoms inside the material itself. And because the charges or the electrons around the nucleus, they are actually moving more or less in the same direction for a big region to have a uniform direction for that motion, and that causes the current in it. So again, that's what causes magnetism. So Mars must have had magnetic field in its past, and that magnetic field was strong enough to basically divert the solar radiation, the cosmic radiation of charged particles toward the poles of the magnetic field, and hence basically protect the planet at least from the solar radiation and the solar wind that all the planets are subject to. That helped retain the atmosphere of Mars, and the pressure was high enough that the liquid water existed on its surface. But because, as I was saying, the planet did not have a lot of mass to begin with, after a while, it ran out of basically radioactive materials in its core, and its temperature started to cool down, meaning that there is less current, because in this case, we're talking about iron and nickel, because they are metals, and since they were molten and moving, so you have a lot of charges in motion creating the current inside the Earth, at least for the case of the Earth, producing that current, and that current is the one responsible for the magnetic field of the planet. So Mars ran out of materials, so it started to cool down, and it did not retain its magnetic field. So now, after that turnout of basically fuel, it was bombarded by the solar radiation that basically stripped it out of its own atmosphere. And combined with the fact that Mars is smaller actually in size, so it did not have strong enough gravitational field. So in other words, it could not retain its atmosphere to begin with the gravity. In this case, it lost all of its atmosphere, or most of it actually, still have some atmosphere in it, which is mainly carbon dioxide. So this explains what's going on with Mars. That's why Mars does not have magnetic field today. If you take the same analogy and try to study Venus, what's going on with Venus? Well, Venus has almost the same size of the Earth. So if the Earth is still heating inside because of radioactive material, so is Mars. So is Venus, I'm sorry. Venus also must have the same thing. So why Venus does not have a magnetic field? Well, it turns out, as I was saying before, because of this model, it's not just the heat inside the core that is responsible for the magnetic field. All the heat does is basically melt iron and nickel. But if these are not moving fast enough to create currents, then in this case, you don't have a strong magnetic field. And Venus spins extremely slowly. So in this case, the motion does not produce enough friction for the charges to be moving, and those charges basically do not create an electric field strong enough to produce any kind of magnetic field on the planet. You see, that's how we understand things, based on the model of what's going on with the Earth and how we came up to be. For the case of Mercury, which is even smaller than Mars, then the problem must have ended a lot earlier than the case of Mars. And that's why there is a difference in crater impacts on the surface of Mercury versus that of Mars. Mercury ended early, so it was subject to a lot of basically impact craters from the early bombardments, just as much as the moon. Okay, and that's why you see a lot of craters on its surface. So we have a good picture of what's going on with the planets, at least based on our understanding of the Earth. And this is how we take what we know and make a model and explain things and actually predict things that we can go and measure. Sure enough, things fit with this model. Okay. Now, because we're detecting one of the things with this model existed before the InSight, and now InSight is not detecting a lot of Mars quakes because of the fact that it does not have a lot of geology on its surface as compared to the Earth, for example. Okay. For the atmosphere now is another story. That's unit 38. The atmosphere is an absolutely different story, and it tells us what's going on. For example, if we're going to model it for planets like Jupiter, for example, I'm trying to understand, because it has a very, very thick atmosphere, and it's spinning, just like the Earth, actually faster than the Earth. So we want to understand what's going on in there. So in terms of an atmosphere for the Earth, Earth does not really have a thick atmosphere compared to, for example, Venus. Venus has a super thick atmosphere, and the other planets don't talk about them, forget about them, the outer planets, okay? So, but its atmosphere has these properties that we know and understand. So we can send balloons and basically start collecting data, namely on temperature, or on density, or how far you are, or on pressure, or chemical composition, and things like that. So this is what we know. The atmosphere is divided mainly into two different layers. The lower layer, which is the troposphere, which is closer to the surface of the Earth, and then the stratosphere is above that. The delineation is slightly over 10 kilometers between them. This is mainly where the jets fly. Okay, it's around this height. What I mean by jets is those big planes that travel between the continents. Okay, so this is where the airplanes travel. And if you have ever had a chance to go on any of them, you will notice that the pressure actually drops, and they have to pressurize the cabin in order for you to feel at ease. Otherwise, the pressure drops so much that your ears start to hurt. And the temperature also drops with it. Look at the temperature. It goes almost to negative 60 degrees. So they need to keep it warm enough for you. And regardless of the day of the year, if you travel on a plane like this one, like the one I'm describing, you probably are going to ask for blankets still. So the point is the temperature drops. And the other critical thing is the density of the air drops too. So they need to keep the cabin pressurized for the pressure, but also for the air so that you can breathe, okay? Because we are at heights that are higher than Mount Everest. We are extremely high at this point. Mount Everest, they extend about 8 kilometers or so in the sky. So this is actually way above that, okay? Of course, if you're on a plane, you don't want to hit the mountains. You want to go at least above the mountains, okay? So this is basically the lower level. And here, this is where most of the weather happens. This is most of the clouds where they form, okay? And they start to condense and fall back as rain. So this is when you look up in the sky and see the clouds, this is the extent with which they are going to be a few kilometers in the sky, okay? Then in the stratosphere, which is divided into several layers, the biggest one, or one of the most important ones, not by far the most important, but at least they have the ozone layer in here. The ozone layer is an important layer. It's mainly made up of oxygen, and oxygen has a special chemical structure, O3 it's called, okay? So in an O3 molecule, basically what happened in this case, you have the normal two molecules of oxygen that normally bond themselves, and but then they split one of the electrons that they share in their chemical bond with the third atom, and now you have a 3 atoms of oxygen making an oxygen and an ozone basically molecule. This is not a really stable molecule. It decays automatically after several minutes, after probably 100 minutes, into normal oxygen, O2, okay? Of course, you need 2 ozone layers to produce 3 oxygen molecules to make the chemical reaction balance. The problem with this process is, as I was saying, is not stable, and it happens this way on its own. So there is actually a regeneration always of the ozone layer and destruction of it naturally. And that's good, because that's the ozone layer actually has a very, very important role, because if it is hit by UV radiation, in other words, the bond itself has an energy that corresponds to the ultraviolet frequency, okay? That breaks it. So if there is radiation coming from the sun that somehow can penetrate through these upper layers of the atmosphere and get in here and happen to be in the UV range is going to be absorbed by the ozone layer and convert the ozone into an oxygen, but the process regenerates, always we have this layer. The problem is that with the human activity and with the so-called CFCs, this material that has a chlorine in it, and chlorine speed up the process of destruction of the ozone layer, and well, we have a problem because there will be not enough ozone molecules left to protect us from the UV radiation that can penetrate. Let me talk about the UV radiation on the left back. The electromagnetic spectrum, basically the vibration of the electric field and the magnetic field, has a big range. One of the ranges that we're familiar with, or at least the one that is useful for us, is between the red color or the red frequency and the violet color or the violet frequency. In this range, our eyes are sensitive to these frequencies, then can interpret the different frequencies with different colors. That's how we evolved, okay? And that's because actually the sun is peaked in this range. It's peaked just in the middle, actually, in the yellow color, okay? Which is just right in the middle in this range. So that's how our eyes evolved. Well, their frequency is higher than the violet. And this includes the UV radiation, ultraviolet radiation. Ultraviolet radiation, we cannot see it. Our eyes are not sensitive in it, but it can damage our skin and damage all organisms, actually, or living organisms. And it's very dangerous. We don't want a lot of it. Actually, if you go on a sunny day, for example, on the beach, you will be exposed to it. So still, some of it is penetrating, some of it still go through, but not as much as it could if this layer did not exist. So the ozone layer itself is a very, very important layer because it protects us from the UV radiation. There is actually worse than the UV radiation, and those are the X-rays. And they still can go through, but not as much, because they're actually blocked by the upper atmosphere in here. And then here, there's actually worse than the X-rays, which is the gamma rays. They're far more energetic. But again, not enough of them, not a lot of them that penetrate the atmosphere. On the other side of the picture, below the red, there is the infrared. The infrared is what you feel heat. And then there is the microwave, which is actually also some sort of, all of them are actually infrared. And then there is the radio waves. Radio waves is what is used in telecommunication, especially in terms of cell phones, in terms of radio telecommunication or TV signal and things like that. So we use that extensively in that range. So those are very long wavelength, very low frequency wavelength. So that's the entire spectrum, okay? So as far as we're concerned, this layer is a very important layer. Above it, right around 80 kilometers or so, you have the ionosphere. The ionosphere is basically the temperature in here, or at least the density is low enough. Remember, the density drops by factor of 99% once you reach about 35 kilometers. That means the air becomes so rare. In this case, you cannot breathe at those temperatures without proper equipment, okay? I mean, maybe if you're trained, I mean, the density will be extremely low. The oxygen will be very low at this point in here. Okay? As a matter of fact, if you go on Himalayas, you really need to be readying yourself, preparing yourself actually for the low pressure and low atmosphere in there. Okay. The point being in here, at this point, the atmosphere will become so thin, and the molecule starts to move faster and faster. And in here, they're so rare because of the low pressure. You're looking at less than 1%, less than 1,000%. This is actually 1,000. This is what, 1,000s of percent. Okay, so this is extremely small. So in this case, the molecules that are left are going to start to moving faster and faster, and the ionization process speeds up until the molecules are moving super fast. At some point, you reach a point where the auroras form. And the auroras are basically charged particles that are delivered by the sun and deviated by the magnetic fields either to the North Pole or the South Pole, depending on their charge. And because they can be mainly electrons or protons, either positively charged or negatively charged. And they interact with the upper layers of the atmosphere and they actually collide with it, producing this ionization and among other things, and actually exchanging the energy in there, and they get dumped in the atmosphere in these regions, protecting the Earth from their danger. The alpha particles are actually another type of charged particles, and the alpha particles are actually mainly the nucleus of the helium. And nucleus of the helium is super heavy compared to a proton or compared to an electron. And if you get exposed to them, they can do a lot of damage. Okay, they can cause a lot of damage. So the atmosphere is actually protecting us in combination with the magnetic field in this fashion. So this is the structure of the Earth. Now, the atmosphere experiences different forces. One of the forces that is of interest to us is the Coriolis Force. Coriolis Force is the one responsible for all kinds of weather and here on Earth and the way that the masses of the air move in the upper atmosphere. Because the fact that the Earth is spinning and these masses of air are moving due to the difference in temperature, the gradient in temperature. So this motion combined with the rotation of the Earth produces this all kinds of effects in here. Okay. Now, Coriolis force is really not a force. It's called a pseudo force. Because forces, we understand interaction of objects. Gravity, for example, requires two objects. It requires the Earth and the object that you're pulling on it. If you push an object or drag it, there are two objects in your interactions. These forces, like for example, if you're sitting on your car, you're not even attached to the back seat. I mean, just sitting, okay? And then somebody accelerates. What is the interaction in this case? It's you only who feeling a force by itself pushing you backward to the seat. That force is actually an inertial force. It's to the fact that you have mass and your mass does not want to accelerate, it wants to resist the acceleration. So that is why it's a pseudo force also, the inertia, the force of inertia, if you want to call it that way. The centripetal force also is another one, or centrifugal force is another one. And that is you're sitting in the car and the car turns this way to the left, for example, you find yourself moving to the right, okay? Your body moves to the right as the car is turning this way. If the car is turning the opposite direction, your body moves in the opposite direction. So this is actually, centrifugal force is actually not really a force, but it's also a pseudo force. And same thing with the Coriolis force is not really a force, it's really a force due to the rotation of the Earth. So the axis of the frame and the frame of reference in this case is actually spinning, and that's why the mass is subject to this force. An example of that is, for example, when you see the bathtub, when you unplug the plug and then the water starts to spin in one direction rather than the other, always in one direction. Same thing with when you flush the toilet, same thing, that's rotation in the upper atmosphere versus the upper hemisphere versus the lower hemisphere. So this explains basically the different weather that we have in the atmosphere and the way the hurricanes form in the northern hemisphere versus the southern hemisphere. And that is because of the rotation and the way that is happening, okay? So it drives a lot of weather, and this is actually similar to what's going on. It helps us at least understand what's going on in terms of the upper layers of the atmosphere, for example, of Jupiter, or that of Saturn, and the planets that have a lot of gases. You see how we take things from planet Earth, from what we know from planet Earth, from what we can measure from planet Earth, from what we can observe from planet Earth, and make basically models for other planets that we don't have access to. They're not handy to us, at least on a day-to-day business affair. Then we come up with models, and sure enough, when we test these models, they seem to work. Of course, we will find exceptions. Let's take, for example, the magnetic field of Jupiter. It's extremely strong because the planet is moving faster than the Earth, but it's not really that fast. It completes one rotation in 10 hours. So it's really not that fast compared to the ratio of the magnetic field. Then in this case, is it because of the currents that are inside? Currents that are inside are made up what type of material? Well, it turns out the hydrogen is the main component of the planet, Jupiter. Hydrogen seems to exist in a weird state inside the planet. And the upper layers of it inside the core of the planet Jupiter, probably it's in liquid form because of the extreme high temperature, but mainly the extreme high pressure. It's hot. I mean, hydrogen itself melts at room temperature. At room temperature, it doesn't melt. I'm sorry, it becomes a gas. So a temperature around 3 Kelvin or 4 Kelvin, it's going to melt. I mean, actually below that, it's going to melt and it's going to not melt. It's going to evaporate. Okay. So we cannot produce hydrogen, for example, in solid state on Earth because we don't have enough adequate, powerful enough technology to make it. But it seems like it exists in this form inside the core of the planet Jupiter because of the extreme high pressure, despite of the fact that there is extreme high temperatures, but the pressure itself plays a role in this case. So could this explain, at this point, we really could not have sent a probe to the deep in the planet, okay? We could not have sent a probe to Huygens, not Huygens, what is the mission? I forgot the name. Part of it was Huygens. Actually, it did not really go way inside in there. As a matter of fact, the magnetic field is too strong for our probes even to go very close from the planet. So again, we have models. We are trying to understand what's going on in there. Hopefully with more data, we can improve on those models because we are in extreme conditions versus the Earth. Because the Earth, at least for our daily experience, sits in the average. So again, these are the units for this week, unit 37 and 38. I know some of you did not have the book. Hopefully, most of you now have received the book by now. That's in a sense why I was a little bit dragging this issue with the exam. The midterm was supposed to happen this week, I think, according to the schedule. So I pushed it a week later to allow for the late people to have their book. So if you did not really have the book, the review will take you a little bit longer time. But you really, honestly, all you need for the midterm is actually in the review. So you really don't need the book to be with you. But the book serves as a great resource when it comes to this review because of the fact that it's going to explain everything if there is a question about it. So if you are in doubt about a specific item, the book can answer it for you. If there is any doubt about anything in the review, please send me a message. Okay? We need to make sure that everything is clear and clean when it comes to the review and you have no doubt about everything, that everything is right. Okay? Please send me a message saying, okay, there is an item in here in the review that it says so and so, and it's telling me the correct answer should be this. However, I believe, why is it that so, or maybe it's, can we explain it differently or something like that? That is going to be very good. If it is something that can be clarified easily, good. If not, we probably are going to go on a one-to-one basis and sit down and get the clarification so that we have it. That's the purpose of the review, to prepare you for the exam, for the midterm. So for those who did not have the book from before, it may take you a little longer, but hopefully you go through it. For those who have had the book, maybe it will take you less than the prescribed time that it says in there. Again, next week, when we have the new type of assignment, which is a project, we're going to talk in detail about the project. And please reach out if you have any questions. If the questions are really of general nature, that would be great to discuss them with the entire class. And if the questions are really related to your own project or your own basically assignments, then we have to have them in a one-to-one basis in a meeting. If during that session we discover that this issue might be of benefit to a lot of people. As a matter of fact, the message that they sent today at 7 a.m. included some of the points that I discovered from meeting with some of you on a one-to-one basis. Okay. And then in this case, either we record the session or we send a notification to everybody basically saying, hey, there is an issue here that hopefully you guys will take care of. Okay. Sounds good.
Yeah, sounds good.
Okay, very good. So I'm going to stop the recording.